Unit 13.1 Microbial fermentation and production of small and macromolecules. Microbial fermentation. The fermentation has always been an important part of our life. The food can be spoiled by microbial fermentation. The foods can be made by microbial fermentation. And the muscle cells uses fermentation to provide us with quick responses. When respiration is not an option, organism must use an alternative mechanism for the regeneration of the limited supply of coenzymes reduced during the oxidation of glucose to pyruvate. If NADPH is not oxidized back to NADP, further catabolism will cease. Consequently, a suitable terminal electron acceptor must be found to take the electron. The fermentation used an organic molecules, pyruvate or a derivatives, as this final electron acceptor, thereby regenerating NADP and allowing catabolism to continue. This results in the formation of reduced waste products such as alcohol and acids that are then excreted from the cells. However, this is very wasteful in terms of recovery of potential energy from glucose, as little or no further ATP is formed. Conversely, complete oxidation to carbon dioxide in conjunction with the oxidative phosphorylation during the respiration can generate a possible further 36 molecules of ATP per glucose molecules. Alcoholic fermentation. Alcoholic fermentation is the process by yeast and certain filamentous fungi and bacteria. It is a two-step process where pyruvate from the EMP pathway or via ED pathway in case of zymomonas is first decarboxylated to acetaldehyde. The NAD is then regenerated during reduction of acetaldehyde to ethanol. Lactic acid fermentation. The lactic acid fermentation is carried out by a few bacteria, including the Streptococcus, Lactobacillus, Lactococcus, and Leuconostoc, along with some fungi, algae, and protozoa. Here, pyruvate, rather than a derivatives of pyruvate, is the electron acceptor and forms lactate. There are two forms of this fermentation. One, homolactic fermentation. The homolactic fermentation is operated by bacteria such as Lactobacillus acidophilus and Lactobacillus casei, which is reduce virtually all pyruvate generated by the glycolysis to lactic acid. This also occurs in animal muscles deprived of oxygen. 2. Heterolactic fermentation. The heterolactic fermentation generates other products along with the lactic acid. The organisms that performed it includes Leuconostoc, mesenteroids, and Lactobacillus brevis. They forms lactate from pyruvate and ethanol from lactic acetyl phosphate, and in certain cases some acetate may be produced. 1. Alcoholic fermentation. Pyruvate to form acetaldehyde, and acid from acetaldehyde in presence of NADH plus H plus to form NAD minus to form ethanol. B. Homolactic fermentation. Pyruvate converted to lactate in presence of NADH plus H to form NAD plus. 3. Heterolactic fermentation. The glucose in the presence of phosphokinase to form pyruvate plus carbon dioxide, and then it forms lactate in the presence of NADH plus H plus to form NAD plus. The pyruvate plus acetyl phosphate to form acetyl-CoA. Then acetyl-CoA to form acetaldehyde in presence of NADH plus H plus to form NAD plus. The acetaldehyde is converted to ethanol in presence of NADH plus H plus to form NAD plus. D. Mixed acid fermentation. The pyruvate is converted to lactate in presence of A2 NADH plus H plus to form 2 NAD plus. In presence of 2x, it forms acetyl-CoA. To acetyl-CoA is converted to acetaldehyde in presence of NADH plus H plus to form NAD plus. Then acetaldehyde is converted to ethanol to form ethanol in presence of NADH plus H plus converted to NAD plus. The acetyl-CoA is converted to acetate. The in presence of pyruvate and 2 lactate, 2 format is it forms 2 format, and the 2 format is converted to carbon dioxide plus 2 hydrogen 2H2 E 2,3 butane diol fermentation. 2 pyruvate is converted to acetolactate, and carbon dioxide is being liberated, and the acetolactate is converted to acetoin, and the carbon dioxide is being liberated. The acetoin is converted to 2,3 butane diol. The NADH plus H plus is converted to NAD plus. Propionic acid fermentation. The propionic acid fermentation, pyruvate is converted to oxaloacetate. Then oxaloacetate to form malate, NADH plus H plus to form NAD plus, and malate is converted to fumarate. Then oxygen is been H2O is been related, and fumarate is converted to succinate. Succinate is again converted in presence of carbon dioxide has been liberated to form pyruvate. G. Butyric acid fermentation. 2 pyruvate is converted to acetolactate CoA. Then acetolactate CoA is converted to butyryl CoA in presence of NADH plus H plus to form NAD plus. The butyryl CoA is converted to butyrate in presence of NADH plus H plus to form NAD plus. And the butyryl CoA is converted to butanol. And acetolactate CoA is converted to acetone plus CO2, and the acetone plus CO2 is converted to isopropanol in presence of NADH plus H plus converted to NAD plus. The common fermentation products derived from pyruvate. Mixed acid fermentation. The mixed acid fermentation is carried out by E. coli and relative facultative anaerobes. The product includes lactate, acetate, small quantities of ethanol and formate. Some organisms could further reduce the formate to hydrogen and carbon dioxide. 2,3 butane diol fermentation is performed by Enterobacter, Erwinia, Klebsiella and Serratia. It is similar to the mixed acid fermentation, but it generates butane diol along with ethanol and acid. The propionic acid fermentation is conducted by several gut bacteria such as species Propionibacterium, some of which are involved in the commercial productions of certain Swiss type cheese and vitamin B12 cobalamin. The propionate is formed from pyruvate via methanoyl CoA pathway, where pyruvate is carboxylated to oxaloacetate and then reduced to propionate via malate, fumarate and succinate. This requires the important cofactor biotin CoA and CO-B12. Butyric acid fermentation. The butyric acid fermentation is carried out by the species Clostridium. These anaerobic spores forms or produce acetone, butanol, propanol, other alcohols and acid. They also ferment amino acids and other nitrogen compounds as well as carbohydrate. The fermentation process. On the commercial scale, there are 5 major groups of fermentation processes. One produce microbial cells or biomass as a product. Baker yeast used in the baking disease is an example of producing cell mass. Other includes single cell protein or for food sources. 2 produces microbial enzymes. 3 produces microbial metabolites. 4 produces recombinant products. 5th processes that modify the compounds that is added to the fermentation process are referred to as a biotransformation. The biotransformation occurs using the inherent enzymatic capability of the most cells. The cells of all the types can be employed to biocatalyze a transformation of certain compounds via dehydration, oxidation, hydroxylation, amination or isomerization. Component parts of a fermentation process. Regardless of type of fermentation, an established process may be divided into 6 basic components. 1. The formulation of media to be used in culturing the process organism during the development of inoculum and in the production fermenter. 2. The sterilization of the medium, fermenters and ancient equipments. 3. Production of an active pure culture is enough quantitative to inoculate the production vessel. 4th. The growth of the organism in the production fermenter under optimum condition for product formation. 5. The extraction of the product and its purification. 6. The disposal of effluent produced by the process. Fermentation medium. The fermentation is a biochemical process of producing the metabolic products by the actions of microorganisms or a group of organisms on a substrate in the presence of a nutrient medium. The fermentation medium represents the raw material for the process. The constituent of the medium may satisfy the element required for the cell biomass and the metabolite production, and there must be an adequate supply of energy for biosynthesis and cell maintenance. The fermentation medium should fulfill the following criteria. Nielsen, Villadsen, Liden in 2003. 1. It should contain a carbon, nitrogen, and energy source. 2. It should contain all essential minerals required for growth. 3. It should contain all necessary growth factors to ensure rapid growth and high yield. 4. It should be of a consistent quality and be readily available throughout the year. 5th, it should causes minimum problem in the downstream processes. 6th, it has no negative effect on the gas liquid mass transfer. 7th, the level and the range of impurities and the potential for generating further undesired products during the process should be very low. All microorganisms require water source of energy. Minerals such as iron, sulfur, phosphorus, and non-minerals such as carbon, hydrogen, oxygen, and the elements and some vitamin plus oxygen if aerobic. The energy for growth comes either from the oxidation of medium component or from the light. Most of the microorganisms are chemotropic, therefore the commonest source of energy is the carbon source, such as a carbohydrate, lipid, and proteins. Some microorganisms also use hydrocarbons or methanol as an energy source. The carbon source has a dual role in the biosynthesis and the energy generation. The fermentation may be defined as a complex medium. Generally, complex medium are used as a fermentation medium. The advantages of applying the complex medium are that they often contains an organic nitrogen source, essential minerals, and different growth factors. The two frequently applied complex medium are corn, steep liquor, and pharma medium. Both contains a very large varieties of amino acids, many different minerals, and many different vitamins. However, there are some disadvantages of complex medium, as a variation in composition and the presence of undesirable compounds. Examples of complex fermentation medium often applied in the fermentation industries. Medium: corn, steep liquor, corn content acetate, amino acid, minerals, and vitamins. Corn starch content starch, glucose. Barley malt starch, glucose. Molasses medium content sucrose, raffinose, glucose, and fructose. Pharma medium: carbohydrate, minerals, amino acids, vitamins, fats, and growth factor. 6. Serum content amino acid, growth factor. Whey, aqueous byproduct of dairy whey industries. Lactose and protein. 8. Yeast extract content pesticide, amino acids, and vitamins. For increased documentation and reproducibility in the fermentation industries, there is a trend towards the application of defined medium with a carbon and energy source, a glucose source, or sucrose or starch, an inorganic nitrogen source, ammonia or nitrogen, a mixture of minerals, and perhaps a few vitamins. Bioreactor. A bioreactor in biochemical engineering, we also use the term like biochemical reactor, biological reactor, fermenter, or microbial reactor, which are all synonymous in a vessel in which the growth and metabolism of the cell takes place. What makes a bioreactor different from the chemical reactor is the presence of living organisms. The bioreactor are commonly cylindrical, ranging size from some liter to cubic millimeter, and are often made of stainless steel. The processes in the bioreactor can either be aerobic or anaerobic. The term bioreactor is often used synonymously with the fermenter. However, in strict sense, a fermenter is a system in which the aerobic process is carried out. Bioreactor design. The bioreactor design is a relatively complex engineering task. The goal of an effective bioreactor is to contain and positively influence the biological reactions. The suitable bioreactor design criteria includes: 1. Microbiological and biochemical characteristics of the cell system, microbial, mammalian, and plant cell. 2. Hydrodynamic characteristics of the bioreactor. 3. Mass and heat characteristics of a bioreactor. 4. Kinetics of cell growth and product formation. 5. Genetic stability characteristics of the cell system. 6. Sterilization and maintenance of sterility. 7. Agitation for mixing of cell and media, and aeration, aerobic fermenters for oxygen supply. 8. Process monitoring and control, regulation of factors like temperature, pH, pressure, aeration, nutrition. 8. Implications of bioreactor design on downward product separation. 9. Capital and operating cost of bioreactor. 10. Potential for bioreactor scale up. In addition to controlling these, the bioreactor must be designed to both promote formation of optimal morphology of organism and eliminate or reduce the contaminations by unwanted organisms or mutations of the organisms. They are wide varieties of bioreactor systems, and any attempt to categorize them by their various attributes will necessarily result in some overlap of system characteristics. Agitation and aeration. Agitation mixing is one of the most important option in bioprocessing. Within a fermenter, there is a need to mix 3 different phases. 1. Liquid phase, which contains dissolved nutrients and metabolites. 2. Gaseous phase, which is predominantly oxygen and carbon dioxide. 3. The solid phase, which is made of cell and any solid substances that may be present. The purpose of mixing: 1. Air bubble dispersion. 2. Mass transfer from air bubbles, that is oxygen supply to the liquid and then to the cell. 3. Supply of nutrient compounds to the cell, more precisely cell agglomerates. 4. Prevention of sedimentation. 5. Securing of heat transfer. 6. Solubility of nutrients components which are less soluble. Agitation is performed in order to mix 3 phases and produce homogeneous conditions. It also promotes the nutrients, gas, and heat transfer. Mixing involves the combination of 3 physical processes: distribution, dispersion, and diffusion. Mixing is achieved using an impeller, usually positioned overhead on a centrally located stirrer shaft, and baffles mounted against the wall of tank. The baffle are usually flat vertical plates. Normally 4 to 6 baffle plates are fitted to the inside cell wall. The type of agitator and the agitator design are required for effective mixing. Various types of agitator have been designed for mixing of gas liquid solid, and gas liquid solid system. Various type of agitators are propelled, turbine, paddle, various disc, and anchor helical disc. Role of impeller agitator: 1. Diminish the size of air bubble to increases the area for oxygen transfer to maintain a uniform environment through the vessel content. Role of baffles: 1. Help in mixing. 2. Mass transfer by increasing turbulence. 3. Preventing vortex formation. 4. Eliminate dead space. The effectiveness of agitation depends on the design of impeller blades, speed of agitation, and depth of the liquid. The agitation involves shear that may damage shear sensitive cells. Thus, maintenance of suitable shear condition during the fermentation is very important. Aeration: the fermentation carried out in the process of oxygen air is known as aerobic fermentation, where in the absence of air it is called as anaerobic fermentation. The aerobic fermentation involves supply of oxygen for cell to meet their specific oxygen demand. Some fermentation operates anaerobically, but the majority are aerobic and requires large quantities of sterile air oxygen. It is also very important in aerobic fermentation that air or oxygen must be dispersed throughout the fermenter. The sterile filter air or oxygen normally enters the fermenter through a sporger system. A sporger is a device for introducing air into the liquid in fermenter. To promote aeration in stirred tank, the sporger is usually located directly below the agitator. The sporger structure affects the overall transfer of oxygen into the medium as it controls the size of the gas bubble produced. 3 types of sporger are commonly used in bioreactor: the porous orifice, also known as perforated pipes, and a nozzle. type of bioreactors. The main functions of bioreactor is to provide a controlled environment for growth of microorganisms or animals, plant cells to obtain desired products. Several types of bioreactor fermenters are used in fermentation process. They may be grouped in several ways: aerobic or anaerobic, batch or continuous, liquid also termed as a submerged, or solid as termed as a surface, and others. The feature of some commonly used bioreactor types are discussed below. 1. Aerated stirred tank reactor. The most common type of aerobic bioreactor in use today is aerated stirred tank reactor. It has mechanically more agitator or impeller within a baffled cylindrical vessels. The operating principle of the stirred tank bioreactor are relatively simple. The function of stirring in a bioreactor are: 1. To eliminate concentration and temperature gradient by homogenizing the vessel content. To disperse gas in the fermentation broth or to aerate the culture. 3. To promote heat transfer between the broth and heat exchange surface. 4. To suspend the cells. The stirred tank bioreactor provides high value of mass and heat transfer rates and excellent mixing. In this system, the high number of variables affects the mass transfer and mixing, but the most important among them are stir speed, number of stirs, and gas flow rate used. The typical figure shows the typical equipment configuration for a stirred tank bioreactor with a single impeller used for aerobic cell culture. During the operation, the sterile medium and inoculum are introduced into a sterile tank, and the air supplied typically enters at the bottom. The sporger, impeller, and baffle present in the reactor determines the effectiveness of mixing and oxygen mass transfer in stirred bioreactor. In the early stage of the process, the warm water may be circulated through the baffles to heat by the system. Later, cool water may be circulated inside them to keep the pores from overheating. As the bioreactor progresses, the bubbles produced by the air supply are broken up by the agitator as they travel upward. At the top of the tank, the exhaust gas is discharged and the product flows back down where it is drained from the tank. Types of bioreactor. The main functions of bioreactor is to provide a controlled environment for the growth of microorganisms or animal plant cell to obtain a desired product. Several types of bioreactor fermenters are used in the fermentation process. They may be grouped into several ways: aerobic or anaerobic, batch or continuous, liquid also termed as a submerged, or solid also termed as a surface, and others. The features of some commonly used bioreactor types are discussed below. 1. Aerated stirred tank reactor. The most common type of aerobic bioreactors in use today is the aerated stirred tank reactor. It has a mechanically moving agitator or impeller within a baffled cylindrical vessel. The operating principle of the stirred tank bioreactor are relatively simple. The function of stirring in a bioreactor are: 1. To eliminate the concentration and temperature gradient by the homogenizing the vessel content, to disperse gas in the fermentation broth, to aerate the culture. 3. To promote heat transfer between the broth and heat exchange surface. 4. To suspend the cell. The stirred tank bioreactor provides high value of mass and heat transfer rate and excellent mixing. In this system, a high number of variable affects the mass transfer and mixing, but the most important among them are stir speed, type, number of stirs, and gas flow rate used. The typical equipment configuration for a stirred tank bioreactors with a single impeller used for aerobic cell culture. During the operation, the sterile medium and inoculum are introduced into the sterilized tank, and the supply typically enters at the bottom. The sporger, impeller, and the baffle present in the reactor determines the effectiveness of mixing and oxygen mass transfer in stirred bioreactor. In the early stage of the process, the warm water may be circulated through the baffle to heat up the system. Later, cool water may be circulated inside them to keep the process from overheating. As the bioreactor progresses, the bubbles produced by the air supply are broken up by the agitator as they travel upward. At the top of the tank, exhaust gas is discharged and the product flows back down, where it is drained from the tank to bubble column. A bubble column reactor is basically a cylindrical vessel with a gas distributor at the bottom. A gas or a mixture of gases is introduced at the bottom through a gas distributor and rise in the form of dispersed phase of bubbles through a continuous liquid phase to provide the efficient contact between gas and liquid phase. The liquid phase can be operated in the batch or continuous form and may move co-currently or counter-currently in the flow direction of the gas phase. There are many variations of bubble column. For example, inserting a tube to stabilize the circulation pattern often forms the loop reactor. This loop reactor permits the processing of large amount of gases and provides a homogeneous flow zone. 3. Airlift reactor. The airlift reactor or modification of a bubble column reactors which generates a medium flow by aerations and circulates the medium in one direction. This is used mainly to avoid excess heat produced during the mechanical agitations. It is ideally suitable for aerobic culture since the oxygen mass transfer coefficient is quite high in comparison to stirred tank reactors. Fundamentally, the airlift bioreactor should be composed of at least two columns, a riser column and a down comer column, and connects between them at the top and bottom of the vessel to circulate the medium. An airlift bioreactor is either a draft tube airlift bioreactor or an external loop bioreactor as shown. The bubbles spurged into a draft tube from an air spurger rises in the riser column draft tube and generate upward medium flow. The medium will reaches the surface pore into the annular space between the draft tube and the enclosing bioreactor vessel down comer and flows downwards. Thus, the medium circulates. The airlift reactor have some of the following advantages. 1. Absence of mechanical stirring arrangement for mixing. 2. Less shearing action compared to stirred tank. 3. Mixing is achieved through the air draft. The bubble column and the airlift reactors are tower type reactors. The tower type reactors make use of kinetic energy of gas bubble to achieve mixing and aeration. The common feature for this type of reaction is the gas supply in the bottom of the reactor. The gas flow creates a density difference in the liquid region which drives the liquid circulation of the pattern. Also, this liquid movement helps to promote the necessary mixing and mass transfer. The lack of moving part, lower power consumption and less shear stress are main advantages for these reactors over the stirred tank reactors for use in bioprocess. 4. Plug flow reactors. In a plug flow tubular reactors, the feed enters at one end of the cylindrical tube and produces a stream leaves at the other end. The long tube and the lack of provision for stirring prevents the complete mixing of the fluid in the tube. Hence, the properties of flowing stream will vary from one point to the another, namely in both radial and axial directions. In an axial tubular reactors, there is incomplete mixing in both radial and axial direction, whereas in ideal tubular reactor, which is called the plug flow reactor, there is assumed to complete mixing perpendicular to the direction of the flow, that is the radial direction, and no mixing in the direction of the flow, that is in axial directions. The absence of longitudinal mixing is the special characteristics of this type of reactor. In the plug flow, the residence time in the reactor is the same for all elements of the fluid, that is the reaction proceeds as the reactant in a plug progresses along the reactor tube. Trickle bed reactor. Fluidized bed bioreactor. The in fluid is bed by reactor. The bed of the solid is taken in the reactor with a perforated bottom and as a facility for pumping the fluid from the bottom. At a lower fluid velocity, the solid remains in the place as the fluid passes through the void in the material. This is known as a packed bed reactor. As the fluid velocity is increases, the reactor will reach a stage where the force of the fluid on the solid is enough to balance the weight of the solid material. At this stage, the gravitational force of particle acting downwards is countered by the buoyancy force by the fluid on going up. Any further increase in velocity of the fluid pushes the particle. They move as if they are fluid. Hence, the bed is called as a fluidized bed. 7. Enzyme reactor. A vessel employed to carry out the desired conversion using an enzyme is called enzyme reactor. Several types of reactors are available. The choice of the reactor type depends on the form of enzyme, free or immobilized, to be used, the kinetic of reactions and the scale of operations. The enzyme reactors can operate batch-wise or continuous. Various important enzyme reactors are a stirred tank batch reactor, which contains all the enzymes and substrate until the conversion is completed. B. The batch membrane reactors, where the enzyme is held within the membrane tube, which allows the substrate to diffuse in and the product to diffuse out. This reactor may often be used in a semi-continuous manner using the same enzyme solution for several batches. C. Packed bed reactor, also called plug flow reactor, containing a settled bed of immobilized enzyme particles. D. Continuous flow stirred tank reactor, which is a continuous operated version. Trickle bed reactor. The trickle bed reactor (TBR) entails the downward movement of liquid and gas over a packed bed of catalyst particle. The term trickle bed is used to mean a reactor in which a liquid phase and gas phase flow concurrently downwards, carrying both reactant and products through a fixed bed of catalyst particles while the reaction takes place. When the gas and the liquid are fed concurrently upward through the catalyst bed, the system is called a flooded bed reactor (FBR) or upflow reactor. Among the three phase gas liquid solid reaction the system encountered in industrial practice, the trickle bed reactor is most widely used. They are employed in the petrochemical and chemical industries, in waste treatment, and in biochemical and electrochemical processing. Membrane reactors. 8. The membrane reactor is a device that combines a membrane and a chemical reactor. The membrane is a barrier that only allows certain components to pass through it. The selectivity of the membrane is controlled by its pore diameter. Membrane reactor combines reactions with separate to increase conversions. One of the product of a given reaction is removed from the reactor through the membrane, forcing the equilibrium of reaction to the right, so that more of that product is produced. There are two main type of these membrane reactors: the insert membrane reactors and catalytic membrane reactors. In the insert membrane reactors, the membrane does not participate in the reaction directly. It simply serves as the barrier to the reactant and some product. A catalytic membrane reactor has a membrane that has either be coated with or is made of material that contains a catalyst, which means that the membrane itself participate in the reactions. In these reactors, and separation occurs simultaneously. 9. Perfusion bioreactor. The perfusion is a continuous or semi-continuous flow of a physiological nutrient solution through a population of cells. It implies that the cell are retained within the culture until a culture unit, as opposed to continuous flow culture chemostat, which washes the cell out with the withdrawal medium. By using a perfused system, one can easily accomplish in situ medium exchange and thus achieves better control of the culture environment, dissolved oxygen, pH, substrate and hormone concentration. Remove toxic extracellular byproduct and constantly recover secrete products to reduces feedback inhibition. The most suitable type of products to be manufactured by using perfusion bioreactor or the non-growth associated secreted product. The perfusion system are most often used for animal cell culture. 10. Mass balance for bioreactors. In the previous section, we derived equation that relates the rate of intracellular reactions with the rate of substrate uptake, the metabolic product formation, and biomass formation. These rates are the key elements in the mass balance for the substrate, the metabolic product, and the biomass, which describes the change in time of concentration of the substrate varies in a bioreactor. The bioreactor may be operated in three different ways. One, batch process, where Fin is equal to F out is equal to 0, that is the volume is constant. The two, the fed batch or semi batch, where F in is not equal to 0, and F out is equal to 0, that is the volume increases. The third, continuous process, where Fm is equal to out, that is not equal to 0, that is the volume is constant. That where F in is equal to volume flow or feed enters bioreactor. F out is equal to volumetric flow rate of output stream. 11. Ideal batch reactor. In batch culture, the sterile growth medium requires or loaded before the process start and then removed at the end. In batch culture, the growth conditions undergo continual changes. The bacterial concentration rises as the substrate concentration diminishes. We can apply the following material balance to any component of the system. The substrate balance is in a batch culture for a component I in a culture volume of V, and change of molar concentration of Ci is equal to the rate of formation of the product. Therefore, d by dt is equal to d by dt is equal to culture volume V into molar concentration of the component I. Ci is equal to net rate of formation of I component due to the chemical reaction in the vessel. Therefore, d by dt into V into Ci is equal to V into CFI. CFI is the rate of product formation. The rate of the product formation depends on the state of cell population, environmental conditions, temperature, pH, medium, composition. After differentiating, we get a d by dt into V into Ci is equal to V into dCi by dt plus V plus Ci into dV by dt. If no liquid is added to or removed from the reactor, and if gas stripped of culture liquid is negligible, then V is constant. Therefore, dV by dt is equal to 0. Then dCi by dt is equal to R into Fi, where RFI is equal to mass I formed by reaction divided by culture volume into time. A similar balance can be formulated for cell concentration by applying general unsteady state mass balance equation. Therefore, dm by dt is equal to m in minus m out plus Rg minus Rc, where m is equal to total mass in tank, m in is equal to mass flow rate in, m out is mass flow rate out, Rg is equal to rate of concentration of mass, and Rc is equal to rate of consumption of the mass. The mass of the cell in the reactor, m is equal to x into V, where x is equal to cell concentration and V is a liquid volume. Therefore, mass rate of the cell growth is equal to Rg is equal to Rx into V. Therefore, Rx is equal to volumetric rate of cell growth. Rx is equal to mu into x, where mu is the specific growth rate. The mass rate of the cell death, Rc is equal to Rd into V into Rd is equal to volumetric rate of cell death. Rd is equal to Kd into x, where Kd is specific depth constant. Substituting this term in general equation, dm by dt is equal to m in minus m out plus Rg minus Rc. Since m in is equal to m out is equal to 0, therefore dm by dt is equal to Rg minus Rc. D into xv divided by dt is equal to mu into x into V minus Kd into x into V. If V is constant, then dx by dt is equal to mu minus Kd into x. 13. Ideal continuous flow stirred tank reactor CSTR. An ideal continuous flow stirred tank reactor is a perfectly mixed continuous flow stirred tank reactor. Such configuration is termed as chemostats. The chemostats ensures a time interval growth environment. The name chemostats refers to the constant chemical environment. When a chemostat is at steady state, the nutrient produced products and cell concentration are constant. In this case, fresh sterile medium is fed to the completely mixed and aerated reactor, and the cell suspension is removed at the same rate. Thus, the liquid volume in the reactor is kept constant. Equation for total mass balance. Generally, unsteady state mass balance equation is equal to dm by dt is equal to m in minus m out plus rg minus rc. For the balance of total mass, rg and rc are zero because the total mass cannot be generated or consumed by chemical reactions. Dm by dt is equal to d into pv by dt. Therefore, m in is equal to f in into p in. M out is equal to f out into p out. Substituting these terms in general mass balance equation, d into pv by dt is equal to f in into p in minus f out into p out. The equation for component mass balance. A similar mass balance based on general unsteady state mass balance equation can be performed for substrate A. dm by dt is equal to m in minus m out plus rg minus rc. Therefore, mass of A in reactor is equal to m is equal to v into ca, where C is the concentration of A. Therefore, dm by dt is equal to d into V into Ca by dt. The mass flow rate of A in M in is equal to F in into Ca in. Therefore, mass flow rate of an out is equal to M out is equal to F out into Ca out. The rate of consumption of A is equal to Rc is equal to R into Ca into V. Therefore, R is equal to rate constant. Since A is not generated in the reaction, so Rg is equal to 0. Substituting this term in the general mass balance equation, d into Vca by dt is equal to f in into Ca in minus f out into Ca out minus Rcav. In similar, mass balance can be performed for cell concentration. A mass balance on cell concentration around the chemostat yield d into xv divided by dt is equal to f in into x in minus f out into x out plus mu into x into v minus kd into x into v. The above equation can be arranged as dx by dt is equal to d into x in plus mu minus kd minus d into x out, where d is equal to dilution rate. Usually the feed medium or sterile, x in is equal to 0 if endogenous medium or death rate is negligible compared to the growth rate. Kd is less than mu, and if the system is at steady state dx by dt is equal to 0, then 0 is equal to d into x in plus mu minus kd minus d into x. If kd is equal to 0, then mu is equal to d. In a chemostat, the cells are removed at the rate equal to that growth rate, and the growth rate of the cell is equal to the dilution rate. By using the monod equation, describe the dependence of the specific growth rate on the limiting substances concentration. The substance concentration S and the cell density x in the bioreactor can be determined. Therefore, mu is equal to capital D is equal to mu m into S divided by K into Ka into Ks plus S. Using the equation 1, we can relate the substrate concentration to dilute the rate. S is equal to Ks into D minus divided by Km minus D. Using the equation, the steady state cell density can be expressed as S equal to Ks into D divided by mu m minus D, where Y into m divided by K bar S is equal to yield coefficient superscript m on K x bar S denotes a maximum value of the yield coefficient. Therefore, S in is equal to substrate concentration of incoming medium. S out is equal to effluent substrate concentration. At a lower flow rate, the substrate is almost completely used by the cell. S to 0, the cell concentration is then X is equal to S in divided by Y. If D increases, X decreases slowly at first in a linear fashion, and then at D is equal to mu m, it drops to 0. So S increases slowly at first, and D increases and approaches S in at D is equal to mu m. Energy balance for a bioreactor. And overall energy balance for a bioreactor during the normal operation is needed to make out an accurate estimation of heating or cooling requirement for a specific process. In bioreactor, overall heat balance includes heat which may be added or removed for following reasons. The fermenter vessel containing medium is heated using steam and held at a sterilized temperature for a period. 1. Metabolic heat generated by the cell. 2. Heat generated due to stirring and agitation. 3. Heat loss due to the evaporation. 4th, if the heat generated in substrate concentration is inadequate to maintain the desired temperature level, heat must be added. The overall energy heat balance can be written as QACE is equal to Qmet minus Qsen plus QSP plus QAG minus QEVAP plus QEX, where QACC is heat accumulation rate at a constant temperature. Qmet is the heat produced by the metabolism of the cell. Qsem is sensible heat given by the flow steam. Qag is heat generated due to the agitation. Qsb is heat generated by the sparging. QEVAP is heat loss by evaporation. QEX is heat generated by the heat exchanger. The heat transformed between the environment and the reactor can be important for small scale vessels but become negligible as volume increases. The heat transferred from the environment can be included in QEX. If the temperature of the reactor is maintained constant, then QACC is equal to 0. Heat exchanger. A heat exchanger is needed to maintain the bioprocess at a constant temperature. Biological fermenter is a major source of heat. Therefore, in most cases, bioreactor needed cooling. The exchange of heat in case of bioprocess is always between fluids that should not mix with each other. So the fluids are kept separated using a highly conducting metal medium. Such a system are generally called as a heat exchanger. Various designs of heat exchangers are used. The heat exchangers used for heat exchange in bioreactor may include an external jacket or coil through which the steam or cooling water is circulated alternatively. 2. Internally located helical or baffle coil. 3. External heat exchanger. Basic operation and process control. Basic operation in fermentation process to produce primary or secondary metabolite involved. 1. Upstream processes. All the operations before starting the fermentation are collectively known as upstream processes, such as sterilization of a fermenter, preparation and sterilization of culture medium, and the preparation of growth of a suitable inoculum of microbial strain. 2. Downstream processes. All the operations after the fermentation are known as downstream processes. It includes the purification of fermented products from fermentation broth, inoculum development, the preparation of a population of microorganisms from a dormant stock culture to a state useful for inoculating a final production. Fermenter is what constitutes the inoculum development stage of a fermentation processes. Generally, a lyophilized or frozen culture is used to inoculate a flask of liquid medium, which is then shaken until enough cells moss has been produced. After the culture is grown, the flask is used to inoculate seed fermenter. The form, age, and the ratio of inoculum are critically important. The inoculum should be active to minimize the lag period, free of contamination, sufficiently large volume, suitable morphological forms, and with a minimum batch variations. The culture medium should be also be very similar to production medium to minimize the lag production. Basic operation involved in typical aerobic fermentation: medium preparation, medium sterilized, inoculum preparation, medium sterilized fermentation, and process control, air filtration, and cell recovery. The process monitoring and control. The performance of a fermentation process depends on the maintenance of a well-defined and controlled environment for biomass and product formation. The environment inside the bioreactor should allows the optimal catalytic activity. The parameters such as temperature, pH, and partial pressure of dissolved oxygen plays a significant effect on the outcome of fermentation. To provide the desired environment, the reactor properties parameters must be monitored and controlled. These parameters can be grouped into three categories: physical, chemical, and biological. The parameter measured or controlled in bioreactor: physical, chemical, biological. Physical: temperature, chemical: pH, biological: biomass concentration. Physical: pressure, chemical: dissolved oxygen, biological: enzyme concentration. Physical: liquid level, chemical: dissolved oxygen, and biological: biomass composition. Physical: gas flow rate, chemical: redox potential, and biological viability. Physical: foam level, chemical: exit gas composition, and biological morphology. Physical: agitator speed, physical: medium flow rate, biological: agitator speed, chemical: conductivity. Physical: medium flow rate, chemical: broth composition. Physical: culture viscosity. The basic principle of control and maintenance involves a sensory system linked to a control system and feedback loop. The control and maintenance at optimum level inside the reactor is mediated by sensor electrodes along with a compatible control system. The sensor used in monitoring the pH, oxygen, foam pressure, redox, and other internal and external parameters. The internal sensors that are in or above the fermentation medium should be steam sterilized. The control of pH is very essential for fermentation process. The fermentation medium often contains buffered salt, usually phosphate, but their capacity to control pH can be exceeded and addition of acid or alkali may be required. The pH can be maintained at a desired value by their automatic addition in response to changes recorded by the pH electrode. Similarly, monitoring of temperature is usually carried out by resistance thermometer or thermometer linked to automatic heating or cooling system. The level of dissolved oxygen and carbon dioxide are determined by using oxygen and carbon dioxide electrode. The formation of a foam in bioreactor is often a major problem. The foam or dispersed of gas in liquid. The formation of foam occurs due to the presence of a surface active agent. The foam or controlled either by chemical or mechanical means. The chemical controlling foams have been classified into antifoams, which are added into the medium to prevent foam formation, and defoamers, which are added to knock out foams once they are formed. The natural antifoams includes plant oil, examples from sunflower and rapeseed. The deodorized fish oil and mineral oils. The synthetic antifoams are mostly silicone oils, polyalcohols, and alkylated glycerol. An ideal antifoam should have the following properties: 1. Should disperse readily and have fast action on an existing foam. 2. Should be active at low concentration. 3. Should not be metabolized by the organisms and non-toxic to the microorganisms. 4. Should not cause any problem in extraction and purification of the product. 5. Should have no effect on oxygen transfer. 6. Should be heat sterilizable. List of monitoring parameters and measuring devices. Monitoring parameters and measuring devices. Monitoring parameter: temperature, measuring device, resistance, thermometer or resistors. Pressure, diaphragm gauges. Flow rate, rotometer or thermal mass flow rate. And monitoring parameters: viscosity, measuring devices, rotational viscometer. Measuring parameter: turbidity, measuring devices, photometer. Monitoring parameter: foam, measuring devices, conductance probe, capacitance probe. Monitoring parameter: agitation, measuring devices, tachometer. Sterilization: If a culture medium or a part of equipment used for fermentation becomes contaminated by living foreign microorganisms, the target microorganisms must grow in competition with the contaminating microorganisms. Thus, not only the medium but also all fermentation equipments being used must be sterilized prior to the start of fermentation, so that they are perfectly free from any living organisms or spores. In case of aerobic fermentations, the air supplied through the fermenter should also be free from contaminating microorganisms. The sterilization is a term referred to any process that eliminates or killed all forms of life. The sterilization can be achieved by applying the proper combination of heat, chemical, irradiation, and filtration. Production of small and macromolecules. The microbes are commercially most important to produce cheese or alcohols, bread, and non-food industries. Cheese production. The discovery of cheese making process is very old and certainly was accidental. The process of cheese manufacturing today follows some of the primitive steps. The milk from any mammals, example cows, horse, camels, whales, guinea pig, and humans, is mixed with renin or a similar enzyme harvested commercially from a mold. Today, the enzyme splits the milk protein casein. The starter culture of a known strain of bacteria that produces desired flavors are added, and the lactose is fermented to acid, which lowers the pH to a point where the cleaved casein precipitate out as a curd. The excess liquid washes away, is drained away, sometimes under pressure, and the semi-dried curd collected. The curd is inoculated with a special bacteria or mold, or both, that are known to give a flavor to the cheese as they grow in and out of the curd. An artificial inoculum of laboratory microbes is used for many cheese, but many cheeses around the world are naturally inoculated by placing them in environment where the air is known to contain microbes that produces a desired cheese. Sometimes additional ingredient like salt and herbs are added to achieve desired flavors in the product. The curd is ripened for various period of time under specific condition of temperature and humidity, often in caves where these environmental factors stay constant. During ripening, the final flavors and consistent of the cheese are produced. At the end of incubation period, the cheese is harvested, packed, and sold. Each microbial strain constrains subtle different chemical flavors to its cheese. Alcohol fermentation. Intense alcohol production by human is known to have been around for at least 10,000 years. Ethanol production process. The term fermentation has a numerous contextual meaning, but in relationship to ethanol production is referred to the metabolism of carbohydrate under anaerobic condition. Any simple or complex carbohydrate can be fermented to produce ethanol. Usually, this fermentation is carried out by certain ubiquitously distributed yeast, but a few bacteria are also able to produce ethanol in commercial quantities. The commercial or industrial production of ethanol is produced as follows. A grain, usually barley, which is rich in complex glucose polymer, complex carbohydrate, is collected and wetted. As it is stored in warm, dry places, the seed germinated, sprout, and release the enzymes that break down or hydrolyze the polysaccharide to simple sugar, which the yeast can metabolize. This process is called a malting. The malt is dried and crushed to improve the extraction of sugar. The dried material can be stored at this stage. In the next step, called mashing, the sprout malt is suspended in water, where the enzyme continues to break down the polysaccharide to release a simple sugar. The liquid and the malt wort containing the dissolved simple sugar is separated from the insoluble material. The hops are added to the wort, which is boiled to destroy any extraneous enzyme, to extract the hop flavor and to precipitate the protein, which could add unwanted flavors to the final product. The hop flowers contains substances that inhibit spoilage microbes and aid in the final clarification of the product. Yeast is then added, pitched, and the mixture is placed in large closed container, usually metal, in large commercial operations. So the fermentation can be processed in the absence of air. The fermentation goes on for about 7 days at a cool temperature, which is optimum for ethanol production. The green beer is usually aged lagered under a variety of conditions for various time as decided by individual brewers. During the aging, the chemical changes occurs spontaneously that subtle alter the flavor of the product. Finally, the product is usually cleared, the yeast removed, bottled and pasteurized. Yeast and other details of fermentation. Each brewer have their own strain of yeast that is known to produce a flavor of their products. The companies go to great length to maintain the genetic purity of their yeast strain, as the wrong mutation can produce subtle changes in the product's flavor. Most ethanol for human consumption is produced by strain of two yeast species, the Saccharomyces Cals bergensis and Saccharomyces cerevisiae, which are characterized as bottom and top yeast respectively, depending on where they settle in the fermenting container. The brews are generally made with the yeast strain that converts more of the available sugar to ethanol, thus lowering the total caloric content of the beer. Wine can be made from any fruits that has enough carbohydrate present to be converted into the enough ethanol to make it a wine. The distilled ethanol products are made from the fermentation of other grains like corn and rye. At the end of fermentation, the material is boiled and more volatile ethanol, which evaporates first, is collected in a concentration form. The combination of unique starting material, the yeast strain, distilled spirits, bread. The rising of bread is due to the fortuitous combination of chemical characteristics. The wheat and several related grains makes up a group of protein called glutens. These proteins have a characteristics of forming long molecular strings when they are worked or kneaded. They bind that bind the bread together in a sticky mass we call dough. The gluten also contributes to delightful flavor imparted to bread during banking. The bread rises due to the activity of contaminating yeast, which metabolizes sugar in the wheat and converts it into carbon dioxide. Because of gluten glue, the carbon dioxide is trapped within the bread, which causes the bread to rise from the pressure of carbon dioxide buildup. This results in the formation of any small bubbles within the bread. When the bread is baked, the protein is denatured and the starch harden into the food we know as bread. The yeast also contributes important flavoring to the bread. Non-food industrial microbiology. The microbes that have been used for about 50 years to produce non-food chemicals for human use in industrial quantities. This section is divided into two parts: the classical industrial chemicals that are be manufactured either by microbes or organic chemical processes, and the biological chemicals that cannot be synthesized by organic chemical processes but only by the living cells themselves. Industrial organic chemicals. Simple organic chemicals like ethanol, acetic acid, vinegar, acetone, butyric acid and lactic acid are readily made either by organic chemicals synthesis or by microbial fermentation. The method of choice depends upon the price of the raw material and on the availability of industrial facility to carry out either processes. That is, in some cases it is cheaper to manufacture ethanol by fermentation, and other cases by chemical conversion from petroleum or natural gases. Immediately preceding the First World War, the process of acetone butanol fermentation by bacteria was discovered. Today, acetone and butanol are more cheaply made from petroleum. But as these natural resources run low in the next century, we may have to return to the microbiological technology. The following is the partial list of organic chemicals made commercially by microbes. A. 2,3 butane, in any diol, buttery test. B. Enzyme. C. The organic acids such as citric acid, lactic, ascorbic acid, vitamin C. These are utilized both as food and in industrial chemical processes. D. Polysaccharides. E. Polybeta hydroxybutyric acid. F. Methane. G. Hydrogen. F. Biological pesticide. Pharmacological industry. The second contribution of microbes to winning a war can through the serendipitous discovery of penicillin by the English microbiologist A. Alexander Fleming in 1929. From this, the following the antibiotic era and the huge pharmacological industry that operate worldwide today. The following is the list of microbial produced commercial pharmacological products: A. Vitamin, B. Amino acids, C. Nucleic acid, D. Antibiotics, E. Alkaloids, F. Steroids. Molecular industrial product. The revolution in molecular biology offers the possibility of yielding a whole new range of microbiological produces through the application of genetic engineering technology. It is now possible to move genes from one organism into a plasmid or into the genome of another organism. Under the proper conditions, the cloned genes can be made to direct the synthesis of their protein product. In this way, substances that has a specific effect on another gene or gene products, but which is normally made in tiny amount in a target organisms, can be made in commercially large quantities. These large quantities can then be used for the therapeutic purposes. A partial list of a therapeutic agent is given below. A. Hormones, insulin, human growth hormones, somatostatin, and interferons. B. Epidermal growth factor. C. Insulin. D. Platelet derived growth factor. E. Proinsulin. F. Fibroblast growth factor. G. Blood clotting factor 13. And H. Transgenic plants and animals. In addition, there is a large industry in productions of genetic engineering materials, which in turn are producing from genetically engineered microbes, plants, or animals. These includes most of the commercial restriction enzymes and plasmids, as well as few other enzymes widely used in the molecular biological research. Most of these industries, some of which are worth millions of dollars, did not exist 15 years ago. New biotechnological industries are appearing all the time. Biotechnology industries are expected to be one of the fastest growing industries in the next century, particularly as the human population ages and as the information from the Human Genome Project comes online. One direction that the biotech industries is going in the constructions of transgenic plants and animals. The transgenic plants and animals are good vehicles for producing human gene products. For example, pigs and goats have human gene incorporated in them. One interesting system involved fusing the desired gene with the milk protein casein of mammals, and then when the animal lactate is produce large quantities of human gene product, which can then be cleaved from the milk protein and purified separately. Sterilization method. All the material, that is vessel, instruments, medium, plants, animals, and microbial culture, must be freed from contamination. The sterilization is a process of inactivation or removal all living organisms from a substance or surface. When a closed system is sterilized, once it retains so indefinitely, since it has no opening for the entry of microbes. But in open system, the continuous sterilization is required to ensure removal of all living entities at their entry point. Some physical and chemical methods of sterilization are given in table. The physical method used to control microbial growth: moist heat, boiling or flowing. Mechanism of action: denaturation. Characteristics: kills the vegetative bacteria and fungal pathogens and many viruses within 10 minutes. Less effective on endospores. Preferred use for dishes, basins, pitchers, various equipments. B. Autoclaving. Mechanism of action denaturation. Characteristics very effective method of sterilization at about 15 psi of pressure 121 degrees centigrade. All vegetative cells and their endospores are killed in about 15 minutes. Preferred use for microbial media, solution, linens, utensils, dressing equipments, and other items that can withstand temperature and pressure. To pasteurization method of mechanism of action denaturations characteristics heat treatment for milk 72 degrees centigrade for about 15 seconds that kills all pathogens and some non-pathogens. The preferred use for milk, creams, and certain alcoholic beverages, beers and wines. 3. Dry heat. A. Direct flaming. Mechanism of action burning contaminants to ashes. Characteristics very effective method of sterilization. Preferred use for inoculating loops. Name B. Incineration. Mechanism of action burning to ashes. Characteristics very effective method of sterilization. Preferred use for paper cups, contaminants, dressings, animal carcasses, bags and wipes. C. Hot air sterilization. Mechanism of action oxidation. Characteristics very effective method of sterilization but requires temperature of 170 degrees centigrade for about 2 hours. You prefer use for empty glassware instruments, needles and glass syringes. Filtrations. Mechanism of action separation of bacteria from suspending liquid. Characteristics the passage of liquid or gas through a screen like materials that traps microbes. More filters. See hot air sterilization. Mechanism of action oxidation. Characteristics very effective method of sterilization but requires temperature of 170 degrees centigrade for about 2 hours. Preferred use for empty glassware, instrument, needles and glass syringes. Filtration separation of bacteria from suspending liquid. Characteristics the passage of liquid or gas through a screen like materials that traps microbes. Most filters in use consist of cellulose acetate or nitrocellulose. Preferred use for sterilizing liquid, toxin, enzyme, vaccines that are destroyed by heat. Cold refrigeration. Mechanism of action decreases the chemical reactions and possible changes in protein. Characteristics has a bacteriostatic effect. Preferred use for food, drugs and culture preservation. Deep freezing. Mechanism of action decreases chemical reactions and possible changes in proteins. Characteristics an effective method for preventing microbial cultures in which cultures are quick frozen between minus 50 degrees centigrade and minus 95 degrees centigrade. Preferred use for food, drug and culture preservation. 3. Lyophilization. And a mechanism of action decrease chemical reactions and possible changes in protein. Characteristics most effective method for long term preservation of microbial culture. Water removed by high vacuum at low temperature. Preferred use for food, drug and culture preservation. Desiccation. Mechanism of action disruption of metabolism. Characteristics involved removal water from the microbes primarily bacteriostatic. Preferred use for food preservation. Osmotic pressure. Mechanism of action plasmolysis. Characteristics results in loss of water from microbial cell. Preferred use for food preservation. Radiation ionization. Destruction of DNA by gamma rays and high energy electron beam. Characteristics not widespread in routine use for sterilization. Preferred use for sterilizing pharmaceutical and medical and dental supplies. 2. Non-ionizing. Mechanism of action damage of DNA by UV light. Characteristics radiation not very penetrating and preferred use for control of closed environment with UV germinator lamp. The chemical agents used to control microbial growth. The chemical agent phenol action method of action: disruption of plasma membrane, denaturation, inactivation of enzyme. Preferred for rarely used characteristics: seldom used as a disinfectant and antiseptic because of its irritating quantities and disagreeable odor. Two phenolics disruption mechanism of action: disruption of plasma membrane, denaturation, inactivation of enzymes. Preferred use for environmental surfaces, instruments, skin surfaces, and mucous membrane. Characteristics: derivatives of phenol that are reactive even in the presence of organic materials. Examples include orthophenol, orthophenyl phenol, and hexachlorophene. Chlorohexidine mechanism of action: disruption of plasma membrane. Preferred use for skin degerming, especially for surgical scrubs. Characteristics: bactericidal or 2 gram positive and gram negative, non-toxic, persistent. Halogens: the iodine inhibits protein functions and it is a strong oxidizing agent. The chlorine forms a strong oxidizing agent, hypochlorous acid, which alters the cellular component. The preferred use for effective antiseptic, available as a tincture and an iodophore. Chlorine gas is used to disinfect water. Chlorine compound are used to disinfect dairy equipment, eating utensils, household items, and glassware. Characteristics: the iodine and chlorine may act alone or as a component of inorganic and organic components. Alcohols, denaturations, and lipid dissolutions. Preferred use for thermometer and other instruments in swabbing the skin with alcohol before and injection. The most of the disinfecting action probably comes from simple swiping away, cleansing or dirt and some microbes. Characteristics: the bactericidal and fungicidal, but not effective against endospores or non-enveloped virus. Commonly used alcohols or ethanol and isopropanol. Heavy metals and their compounds, denaturation of enzymes and other essential proteins. Preferred use for silver may be used to prevent gonococcal eye infections, mercurochrome, disinfect skin and mucous membrane. Copper sulfate is an algicide. Characteristics: the heavy metals such as silver and mercury or germicidal or antiseptics. Surface acting agent: soap and acid anionic detergents. The mechanism of action: mechanical removal of microbes through scrubbing. Preferred use for skin degerming and removal of debris. Characteristics: many deodorant soaps contains antimicrobials such as trichlocarbons. 2. Acid anionic detergents. Mechanism of action not certain, may involve enzyme inactivations or disruptions. Prefer use for sanitizers in dairy and food processing industries. Characteristics: the wide spectrum of activity, non-toxic and non-corrosive, fast acting. Chemical agents: cationic detergents, quaternary ammonium compounds. Method of action: enzyme inhibition, protein denaturation, and disruption of plasma membrane. Preferred use for antiseptic for skin, instruments, utensils, and rubber goods. The characteristics: bactericidal, bacteriostatic, fungicidal, and virucidal agents enveloped viruses. Examples of quartz or Zepiran, TM, and Cipacol. Organic acids. Mechanism of action: the metabolic inhibition, mostly affecting mold action, not related to their acidity. They were preferred for sorbic acid and benzoic acid, effective at a low pH. Parabens, much used in cosmetics, shampoos. Calcium porphenate, used in bread, ale, or used mainly as antifungals. Characteristics: widely used to control molds and some bacteria in foods and cosmetics. Aldehyde, prevents mechanism of action, protein inactivation. Preferred use for glutaraldehyde. Sidex is less irritating than formaldehyde and is used for sterilization of medical equipments. And characteristics very effective antimicrobials. Glutaraldehyde is considered a liquid sterilant, gaseous sterilant. Mechanism of action denaturation. Preferred use for excellent sterilizing agent, especially for objects that would be damaged by heat. The characteristics ethylene oxide is most commonly used. Oxidizing agent. Mechanism of action oxidation. Preferred use for contaminated surface, some deep wounds in which they are very effective against the oxygen sensitive anaerobes. Characteristics. The ozone is gaining attention as a potential replacement for chlorination. Hydrogen peroxide is a poor antiseptic but a good disinfectant. Metabolite production. The microorganism produces an exceedingly large number of metabolites during their growth using usually cheap substrates. Some of the metabolites are as follows: 1. Acetone, butanol; 2. Alcohol; 3. Antibiotics; 4. Enzymes; 5. Organic acids. Examples: lactic acid produces 40,000 tons per year. Critic and 3 lakhs tons per year. 4. Amino acids. Examples: glutamic acid 3 lakhs tons per year, lysine 40,000 tons per year, etc. and vitamins, etc. Of this production of first 4 groups of metabolites is briefly described below. Acetone butanol production. The acetone butanol production is a strictly anaerobic process due to the strictly anaerobic Clostridium acetobutylicum. The process are industrialized to produce acetone, used as a solvent for cordite for explosive manufacture during the World War I. Later it was used to produce a butanol, which has varied application. But at present both acetone and butanol are obtained by chemical synthesis, and this fermentation is rarely used. The Clostridium acetobutylicum is a spore-forming bacteria whose strain differs in the ability to utilize various substrates. Examples: potato, molasses, corn, etc. The fermentation yields a few products, of which acetone, butanol, and ethanol are the major ones. Generally, the strains are developed to produce the highest possible ratio of butanol over acetone and ethanol. During the fermentation, the starch is digested to yield glucose, which is then metabolized to yield butanol and acetone. The culture stocks are usually maintained on dried soil, and continuous transfer of culture is avoided. The cornmeal media is prepared by grinding degermed embryonated corn to fine powder. 8 to 10% of this cornmeal is heated to gelatinize the starch. The molasses medium contains 6% of sucrose, to which are added ammonium sulfate, the calcium carbonate, superphosphate, and sometimes corn steep liquor. The corn media is used for fermentation by Clostridium acetobutylicum, while molasses medium is fermented by Clostridium acetobutylicum. The fermentation passes through the following 3 phases. First, rapid bacterial growth, the production of acetic and butyric acid, and evolution of carbon dioxide and hydrogen. Initially, hydrogen is a major component of gases. For 13 to 17 hours of incubation, it rapid conversion of acid into acetone and butanol, leading to fast decline in the acidity of a broth. This is called acid break, and marked decrease in gas evolution and acetone and butanol production. Glucose on glycolysis to produce pyruvic acid, and liberation of carbon dioxide to form acetyl CoA, and acetyl CoA to form acetic acid, and acetyl-CoA to form acetyl-CoA, and acetyl-CoA to form acetone, and acetone to form isopropanol. Acetyl-CoA to form crotonyl-CoA, crotonyl-CoA from butyryl-CoA, butyryl-CoA to form butyric acid from N-butanol. An outline of biochemical reaction leading to the production of N-butanol, acetone and isopropanol during acetone-butanol fermentation. The final broth contains about 2% of acetone, ethanol and butanol, which represents about 30% conversion of carbohydrate. Typically, corn medium yields butanol, acetone and ethanol in the ratio of 6:3:1, while for molasses, the medium, these values are 6.5:3:5. The recovery of a product is achieved by the distillation process, usually by the beer still, which operates in a continuous mode. This yield approximately 40% weight by weight. The total mixture solvent. Initially, solvent are separated by fractional distillation. Industrial alcohol. Ethanol. The ethanol used for industrial, laboratory and fuel purposes are called industrial alcohol. Ethanol have now become synonymous with energy. The various substrates used for ethanol production and their processing is briefly summarized below. 1. Sugar crops. Example: sugar cane, sugar beet, sorghum, etc. provides a good substrate. The juice from these crops contains sugar. One sugar crop, example sugar cane, sugar beet, sorghum, example etc. provides a good substrate. The juices from these crops contain sugar. Example sugar cane juice has about 12% of fermentable sugar and can be used directly from fermentation. However, they can be stored in later use only after conversion to a syrup. In Brazil, the sugarcane juice cleaned by screens and sedimentation is used for fermentation. 2. Byproduct sugar from crop processing. Example: molasses, sweet sorghum syrup and spent sulfate liquor are the most common substrate. Molasses C grade obtained after sugar recovery contains about 35% of sucrose, 19% other reducing agents and 14% other organic substances. Thus, the total fermentable sugars are nearly 50 to 55%. The molasses is first suitable diluted, then treated with 0.5%. By weighing concentration sulfuric acid at 70 to 95%, 5 degrees centigrade, mainly for removal of calcium, salt and acidification, and used for fermentation. 3. Cereals like maize, wheats, sorghum, etc. contain 60 to 75% weight per weight starch, which on hydrolysis produces a glucose in the ratio of 9:10. Generally, starch is a mixture of alpha amylose 20 to 30% of water soluble linear polymer and amylopectin 70 to 80% of water insoluble branched polymer. The conversion of starch into glucose is usually achieved by cooking process aided by the enzyme. The seeds are powdered and the resulting meal is mixed with water in the ratio of 1:2.5 to 3. Alpha amylase is then added and the temperature is raised by steam injection to 105 to 105 to 110 degrees centigrade and held for about 20 minutes. During this period, the starch grains becomes dissolved to form a viscous suspension gelatinization due to the cooking effects of heat. At the same time, the alpha amylase digests partially some of the starch molecules and this reduces the viscosity of the suspension, and the process is called liquefaction. The suspension contains solubilized starch molecules and dextrins, short chain of glucose unit. The suspension called mash is cooled to 85 to 90% and more alpha amylase is added to complete the process of liquefaction, which takes about for 90 minutes. The total dose of alpha amylase is about 1.5 kilo per ton starch. The mash is cooled to 55 to 60 degrees centigrade and 1.5 to 3.5 1 glucoamylase per ton of starch is added to produce a glucose from dextrins and maltose. The reaction duration is usually 2 days, and it achieves the dextron equivalent of 99. This process is known as a saccharification. It continues during the fermentation. The starch example powder, see meal tuber, etc. on in presence of enzyme hydrolyzes 50 to 60 degrees centigrade to form glucose, and in presence of yeast glycolysis 30 to 35 degrees centigrade to form pyruvate, and in presence of yeast 30 to 35 degrees centigrade pyruvate decarboxylase to form acetaldehyde, and in presence of yeast 30 to 35 degrees centigrade alcohol dehydrogenase to form ethanol recovered by distillation. A summary of the step is a production of ethanol from a starch substrate for tubular like a cassava, yams, potato, etc. are rich in starch, calcium 30% on fresh weight base. Cassava tuber are washed, mashed to pulp, and subjected to liquefaction and saccharification in a matter similar to the cereals. The cassava tuber roots can be air dried to 15% moisture and stored, but tuber chips or meals are better for storage. 5. Cellulosic substrate are the most abundant. They are available as forestry product. Example, wood or as waste. Example, stovers, basasi, sawdust, paper waste, etc. The acid hydrolysis of cellulose is technically possible and was used during the war. The enzyme hydrolysis has presented problem. A more promising approach appears to be the direct conversion of suitable pre-treated cellulose into ethanol by the mixed culture of cellulotic and fermentating bacteria. Some thermophilic Clostridium species are rather promising. The pre-treatment of cellulosic biomass may be either physical or chemical, and it is aimed at reducing the size of the substrate to help in cellulose hydrolysis. Typically, the fermentation of 100 grams glucose by selected strain of Saccharomyces cerevisiae and Saccharomyces carbagensis yields 59 to 69 grams ethanol, the theoretical limit being 51.5 grams. C6H12O6 gives C2H5OH plus 2 CO2. Both batch and continuous fermentation processes are used, and often yeast cells are recycled to save the substrate use up as a cell matter. The continuous process uses 3 to 5 closed vessels. Ethanol concentration increases from calcium. The 4% in the first vessel to calcium, 10% in the final vessel. The productivity ranges from 10 to 20 kg ethanol per meter square per hour. In contrast, the batch process productivity ranges between 1.5 and 3 kg ethanol per meter square per hour. However, the final yield are much higher in the batch process, which is most commonly used. Generally, ammonium sulfate or urea, N source, and the salt of phosphoric acid, P source, are added to the substrate. The most commonly, the temperature during the fermentation is 32 to 38 degrees centigrade, and the pH is maintained between 4.5 to 5. In large fermenter vessels, some forms of cooling are necessary. As ethanol level rises, both ethanol production and yeast cell growth are progressively inhibited, and eventually cells begins to die. In a batch fermenter, the following 4 successive stages occurs. 1. Rapid growth of yeast and parallel increase in ethanol production. 2. Decline in yeast growth coupled with a slower increase in ethanol production. 3. No yeast growth but low level of ethanol production. Yeast cell begins to die. 4. Finally, ethanol production stops. In general, the yeast growth stops at 6 to 9% weight by volume ethanol, but ethanol production, at least in some strains, may continue up to 15% ethanol or higher. Ethanol inhibition can be relieved by continuous removal of ethanol. The commercial process called biostill technique passes cell-free broth through an evaporation chamber for ethanol removal, and the medium is then fed back into the fermenter. The ethanol recovery is based on distillation. 1. Broth is distilled in a beer column to yield 85% weight by volume ethanol. The next step of rectification gives 96.5% ethanol, which is then 3. Dehydration to 99.4% using the benzene or cyclohexane if ethanol is to be used as a fuel blend. But many car engines can use 95% of ethanol, making the final dehydration unnecessary. The wastewater effluent can be used directly on land used for anaerobic digestion for methane generation, evaporated to dry scrub to be used as a animal fuel or used as a substrate for fungal biomass production. Antibiotics. The antibiotic are metabolites having preferential antimicrobial activity. Therefore, they are widely used for curing of human ailment caused by the microorganisms. But some of the antibiotics have anti-tumor activity as well. As the antibiotic penicillin was discovered by Fleming in 1929, but its commercial production could commence only during early 1940s. Although more than 7,000 antibiotic compounds have been isolated, only 100 or so are being used to treat human, animals, and plant disease. The antibiotic compounds are used either in their natural forms or as a semi-synthetic derivatives. The latter are usually produced by isolating the antibiotic nucleus and subjecting it to chemical modification. The antibiotics are produced by both fungi and bacteria, but over 50% of them are obtained from Streptomyces alone. Antibiotics. Amphotericin B, produced by Streptomyces nodosus. Activity antifungal. Chemical nature polyene. Bactericin, produced by Bacillus subtilis. Activity gram bacteria. Pesticide. Cephalosporin, produced by Cephalosporium. Activity gram positive and gram negative bacteria. Pesticide. Chemical nature peptide. Cyclohexamide. Streptococcus griseus. Antifungal. Antibiotic. Fungimycin, produced by Streptococcus colicolor. Activity antifungal. Chemical nature polyene. Gentamicin, produced by Micromonospora purpura. Activity gram positive bacteria. Aminoglycoside. Germicide, produced by the Bacillus brevis. Activity gram positive bacteria. Chemical nature peptide. Antibiotic Griseofulvin, produced by Penicillium griseofluvam. Activity gram positive gram negative bacteria. Chemical nature spironolactone. Antibiotic kanamycin, produced by Streptomycin kanamycetes. Activity gram positive and gram negative bacteria and Mycobacterium. Chemical nature aminoglycoside. Neomycin, yes, Frediae. Activity gram positive and gram negative bacteria. Aminoglycoside. Chemical nature. Pimaricin, produced by S. natalensis. Activity anti-tumor. Chemical nature polyethylene. Penicillin G, produced by P. chrysogium. Chemical activity gram positive bacteria peptide. Chemical nature peptide. Polymyxin B, produced by Bacillus polymyxa. Activity antifungal. Chemical nature peptide. Streptomycin S. griseus. Activity gram positive gram negative bacteria and Mycobacterium. Chemical nature aminoglycoside. Tetracycline, produced by Streptomyces species. Activity gram positive gram negative bacteria. Chemical nature tetracycline. Trichomycin, produced by S. hachijoensis. Activity antifungal. Chemical nature polyene. Inoculum. The high yielding strain is a prerequisite for antibiotic production. Therefore, constant strain improvement is an integral part of commercial production activity. The improved strain strains are kept in long-term storage from which the small quantities is taken to initiate the inoculum development. The inoculum development begins on solid media and subsequently liquid media are used. The media used are specific for inoculum development. The inoculum is prepared usually in the form of a spore suspension which is transferred into the fermenter by using in a metal vessel that is attached to the fermenter. The spore suspension may be blown into the fermenter by using a sterile air in, and it may be allowed to run in under gravity. As a rule, the number of stages between the preserved material inoculum stage is kept to a minimum the risk minimum to minimize the risk of organism losing its high yield. Fermenter. The antibiotics are generally produced in stainless steel fermenter, 30,000 to 2 lakhs medium used in the batch or fed batch medium. The agitation is mostly in impeller, but airlift system is used. The water is used to maintain the temperature between 24 to 26 degrees centigrade for most antibiotic procedure. Generally, the fermentation at above atmospheric pressure. This reduces the contamination risk and enhances the oxygen supply in the medium. The sterile air is supplied as per need, and for some processes, example penicillin production, the material need to be added throughout the process. In most cases, it is critical to prevent contamination and suitable cleaning procedure between fermenter runs must be adhered to. The final stage fermenter is preferable used for antibiotic production for longest possible period. That the stages of fermentation are designed for considerable microbial growth. Typically, these are carried in fermenter for smaller size. One or more seed stage may be used depending on the process and they to produce the maximum amount of biomass in the correct physiological state of high antibiotic productivity and introduced to the final stage fermenter. Production media. Antibiotic production employs a varieties of media, a different one for which each stage of operation. A considerable research effort is directed at developing seed stage and production media to reduce consist and to enhance the yield. A typical production media has about 10% weight by volume solids. Generally, yields as much higher on complex media. In some cases, a suitable precursor for antibiotic is also provided. Example for penicillin G production, phenyl acetic acid or phenoxy acetic acid is used as a precursor. Since the antibiotic or secondary metabolites, the production media is so designed that a key nutrient becomes limiting at a critical stage to initiate the secondary metabolism in the organism. The nutrients to be made limiting depends on the processes. Example, glucose for penicillin production and phosphate for several antibiotics produced by streptomycin. In contrast, the seed stage medium is devised for rapid growth and to prevent the antibiotic production and sporulation. When the seed culture reaches the correct stage, that is the stage suitable for optimal production in the final production stage, in many cases it is the log phase. About 0.1 to 20% of final stage volume is transferred into the production fermenter. Rigorous contamination control is essential for this stage. In most production process, the production fermenter is run in a fed batch mode in which a nutrition, example glucose, is added continuously throughout the fermentation to enhance the duration of antibiotic production. In such a case, the small volumes of broth are usually withdrawn to check increase in the volume of broth in the fermenter. The anti-foaming agent are added at appropriate stage of fermentation to minimize foaming. The silicone, vegetable oils, etc. are used for this purpose. The selective microbiological, physical and chemical features are monitored during the fermentation in order to achieve a proper control on the process. The nutritional status of a broth is monitored regularly to adjust the nutrition and precursor if any feeding in fed batch system. The microprocessor and computers are commonly used to record all the parameters and processes changes and to control various operations like sterilization, etc. At the end of the final production stage, incubation, the broth contains only a low concentration, 3 to 35% of total solute in the broth of the antibiotic. The initial step in the antibiotic recovery is separation of cell from the broth. This is usually achieved by filtration or centrifugation, but in some cases the whole blood is used for extraction. The antibiotic isolation and purification employs solvent extraction, ion exchange, ultrafiltration, reverse osmosis, precipitation and crystallization. Enzymes are proteins which catalyze specific biochemical reactions in a very efficient manner. The enzymes have been used for thousands of years as a crude animal and plant preparations or as a whole microorganisms which can grow on substrate. The industrial productions of enzyme dates to 1894 when fungal diastase was smoked for pharmaceutical use. Initially, enzymes were produced by solid-state fermentation, which is still used in Japan. But most current production processes are based on submerged culture, which are effectively aerated. The oxygen requirement is generally as high as that for antibiotics. Most industrially important enzymes are extracellular, which makes their recovery from broth relatively easier. A few enzymes are produced on a large scale and used in commercial operations. Of these, bacillus protease, glucoamylase and amylase are produced in large quantities, ca 300 tons per year for each. In addition, many enzymes are produced on much smaller scale and are mainly used for research, biochemical and medical investigation. List of some enzymes used for commercial activities. Enzymes alpha amylase source, Bacillus ligniformis, Bacillus amyloliquefaciens. Application: hydrolysis of starch to dextran. Uses in the form of extracellular and soluble. 2. Glucoamylase source, Aspergillus niger. Application: dextran hydrolysis to glucose. Uses in the form of extracellular and soluble. 3. Xylose glucose isomerase. Alkaline protease sources: Bacillus ligniformis, Bacillus subtilis. Application: detergents, protein digestion. Uses: extracellular and soluble. Enzymes: neutralase protease. Sources: Bacillus aminoliquefaciens, Bacillus subtilis. Applications: protein digestion in brewer substances. Uses in the form of extracellular and soluble. Acid protease, example rennet. Sources: Aspergillus niger. Application: milk coagulation and cheese flavor enhancement. Uses in the form of extracellular and soluble. Enzyme pectinase. Sources: Aspergillus niger and Bacillus subtilis. Application: pectin hydrolysis in fruit juice. Uses in the form of extracellular and soluble. Enzyme glucanase. Sources: Aspergillus niger, Aspergillus subtilis. Application: in fruit juices in the form of extracellular and soluble. Enzyme cellulase. Sources: Aspergillus niger, Trichoderma resci, Rhizopus species. Application: cellulose hydrolysis in fruit juice. Uses in the form of extracellular and soluble. Lipase enzyme. Sources: Aspergillus niger. Application: detergent, lipid hydrolysis. Uses in the form of extracellular and soluble. Enzyme lactase. Application: milk lactose hydrolysis to glucose plus galactose. Uses in the form of immobilized on glass beads. Strain improvement. The enzyme yield can be increased by careful selection of organism, improvement in fermentation process, strain development, and refinement of downstream processing. The end use of the product and the condition under which it is to be used will dictate the choice of organism and product purity. But the ultimate objectives of the strain improvement is to obtain regulatory mutant for the concerned enzyme so that its production is no more subjected to the normal regulation. When immobilized cell are to be used, the cell lysis must be absent and all the enzymes should be retained within the cells. Fermentation. The inoculum is developed in several stages as is the case with other fermentation. The organism may then be multiplied in one or more seed tank stages. The medium used for these stages is rather rich to support good growth. The seed tank culture is finally inoculated into the production stage fermenter 25,000 to 1 lakh. The production medium is almost always complex and it is devised to maximum yield of the enzyme. Appropriate measures must be employed to ensure contamination control. Biomass of organism begins to increase early during the fermentation, while enzyme activity shows significant increase about midway through the fermentation. The end of the fermentation is signaled by cessation of enzyme synthesis. Isolation purification. Isolation purification is done immediately after the termination of fermentation in a manner that retains the enzyme activity. If the cells are to be used for immobilization, the biomass is located and treated to make it ready for use. The extracellular enzymes are recovered directly from broth, while the enzyme localized within the cells are isolated by rupturing the cells. The enzyme purification is based on various techniques whose efficiency or cost differ widely. The process used will mainly depends on the purity needed and the cost that is acceptable. The microbial growth kinetics. Microbial growth is the result of both cell division and change in cell size. The microorganisms can grow under a variety of physical, chemical, and nutritional conditions. It is the suitable nutrition medium. The organism extracts nutrients from the medium and converts them into biological compound. A part of these nutrients are used for energy production and part are used for biosynthesis and product formation. Thus, microbial growth is an orderly increase in the quantity of cellular constituent, that is cell mass and number. It depends on the ability of the cell to form new protoplasm from nutrients available in the environment. The microbial growth is a good example of an autocatalytic reactions. Microbial batch growth. When a microbe such as a bacterial cell is inoculated into a flask containing fresh culture medium and incubated, it enters a rapid growth phase during which the microbe divides and increases its population in the flask medium. Since the microbes are not transferred to a new medium or no fresh nutrients are added to the medium, the increasing population of microbial cell after sometimes enters into a stationary phase with the exhaustion of required nutrient and the accumulation of inhibitory end product in the medium. Eventually, the stationary phase of microbial population culminates into death phase when the viable microbial cell begins to die. A batch culture can be closed system. Growth kinetics in batch culture. The growth in batch culture can be divided into 4 distinct phases. They are lag phase, log phase, stationary phase, and dead phase. The lag phase. During this phase, there is no increase in cell number. It is a period of adequate of cell to a new environment. There is no change in the number but an increase in mass. Thus, in this phase, the microorganisms are not dormant. The length of the lag phase is determined in part of the characteristics of microbial species and in part by conditions in the medium. The multiple lag phase may sometimes be observed when the medium contains more than one carbon source. This phenomenon is known as a dauxic growth. It occurs due to the shift in metabolic pathway in the middle of the growth cycle. After one carbon source is exhausted, the cell adapts their metabolic activities to utilize the second carbon source. 2. Log phase. The cell growth rate is the highest in the log phase. In this phase, the cell mass and the cell number increases exponentially with time. Since growth is exponential in nature, when the cell concentration is plotted versus time on this semi-log plot, the log phase results in a straight line. The logarithmic growth phase is also known as exponential growth phase. The log phase is a period of balanced growth in which all components of cell growth at the same rate. In balanced growth, the cell can modulate the effect of external conditions and keep the cell composition steady despite changes in the environmental condition. That is, composition of biomass remains constant. The exponential growth is the first order rate reactions. The rate of increase in biomass is correlated with the specific growth rate mu, and the biomass concentration or the cell number x. The specific growth rate, a measure of rapidity of growth, has dimension t to the power of -1. dx by dt is equal to mu into x. The integration of this equation, the limit x0 at time t is equal to 0 and x at some time t, gives in into capital X divided by x0 is equal to mu t, or x is equal to x0 into e to the power of mu t. Taking the natural log in x is equal to in into x0 plus mu t. In the general equation, the straight line graph for cell in exponential phase, the plot of natural log of a biomass concentration against the time, a semi-log plot should hold a straight line with a slope equal to mu. The exponential phase is followed by the deceleration phase. This phase is of unbalanced growth rate of synthesis of a cell component varies to each other. In this phase, the growth deceleration due to entire depletion of one or more essential nutrient of the accumulation of toxic byproduct of growth. 3. Stationary phase. The stationary phase start at the end of a deceleration phase when the net growth rate is 0, no cell division, or when the growth rate is equal to the death phase. The cell growth rate has leveled off and become constant. The number of cell multiplying equals the number of cell dying. Even though the net growth rate is 0 during the stationary phase, the cell are still metabolically active and produces secondary metabolite. There is death phase. In this phase, the number of cell dying is greater than the number of cell multiplying. The cause of death decline phase is usually that the cell has consumed most of the nutrient in the medium and there is not enough left for sustainable. The kinetics of cell death. The cell death is the first order process. RD is equal to KD into N, where RD is the rate of cell death, N is the number of viable cell, and KD is the specific death constant. In closed system, rate of cell death is equal to the rate of decrease in cell number. Therefore, from the above equation, RD is equal to D into capital N divided by minus D into capital N divided by dt, that is equal to KD into N. If KD is constant, we can integrate the above equation to derive an expression for capital N as the function of time. Therefore, capital N is equal to N0 into e to the power of minus KD into t, where N0 is the number of viable cell at time 0. Taking natural logarithm of both side of equation, we get in N is equal to N0 minus KD into t. Effect of substrate concentration in batch culture. During the growth phase of batch culture, the specific growth rate of cell is dependent on the concentration of substrate in the medium. Often a single substrate extracts a dominant influence on growth rate. This substrate is known as a growth rate limiting substrate. The growth limiting substrate is often the carbon or nitrogen source. The specific growth rate is generally found to be function of 3 parameters: the concentration of the growth limiting substrate S, the minimum specific growth rate mu max, and a substrate specific constant Ks. Therefore, mu is equal to mu max into capital S divided by Ks plus S. This equation is generally called as a monod equation. The capital S is the substrate concentration at which half the maximum specific growth rate is obtained. Therefore, mu is equal to 0.5 mu m. Therefore, Ks is equal to the Michaelis constant in enzyme kinetics. If there is an excess of all substrate, then mu is equal to mu m, and the culture is in the log phase and its maximum growth rate. The specific growth rate is independent of substrate concentration if excess substrate is present. Taking the reciprocal value in the monod equation and rearranging the equation, 1 divided by mu is equal to Ks plus capital S divided by mu max into capital S, or 1 by mu is equal to Ks divided by mu max into capital S by plus capital S divided by mu max into capital S, and 1 by mu is equal to Ks divided by mu max into 1 by S plus 1 by mu max. The plot of 1 by mu against 1 by S produces a straight line with the intercept on the y-axis at 1 by mu max and slope equal to Ks divided by mu max. Growth yield coefficient. During the development of batch process, the key growth parameter can be determined that enables the production of a given microbial product to be optimized. Whether it is the biomass itself or specific metabolite, an important parameter is the yield coefficient. In the case of biomass production, the yield coefficient, termed growth yield coefficient, relates to the quantity of biomass produced per grams of substrate utilized. Therefore, the higher the growth yield coefficient, the greater percentage of original substrate converted into microbial biomass. Therefore, y capital X divided by S is equal to delta X divided by minus delta S, where delta X is equal to change in biomass concentration grams per liter. Y X bar C by S is equal to yield coefficient G biomass per gram substrate utilization. Therefore, capital S is equal to change in substrate concentration G bar L. At the end of the batch growth, we get appropriate or observed growth yield. It is different from true growth yield. The growth yield coefficient measures experimentally is affected by the maintenance energy required of the microbes. The concept of maintenance energy arises due to recognition of the fact that the microbes consumes a certain amount of energy to carry out basic function within the cell. The cellular maintenance represents the energy expenditure for various cell energetic requirement for survival, such as repair of damaged cellular component, motility, transport of material and product in and out of the cell. The endogenous metabolism of biomass component is used for maintenance energy. The endogenous metabolism describes reaction in cell which consumes the cell substances during the microbial culture. If the observed growth yield coefficient for the microbial growth is y x bar S is equal to delta X divided by delta minus delta S, and the substrate consumed fed batch culture. The batch culture refers to a closed system in which a sterile growth medium is loaded before the process starts and then removed at the end. In batch culture, the growth condition undergoes continual change. The microbial concentration rises as the substrate concentration diminished. An enhancement of closed batch process is the fed batch culture. In fed batch culture, the nutrients are added incrementally at various times during the culture. The growth medium is not removed until the end of the process. The fed batch culture is usually used to overcome the substrate inhibition or metabolite repression by intermittent feeding of the substrate. If the substrate is inhibitory, the intermittent addition of the substrate improves the productivity of the fermentation by maintaining the low substrate concentration. The fed batch operation is also called the semi-continuous system. In some fed batch operation, the part of the culture volume is removed at certain interval. Since the reactor volume is limited, this operation is called the repeated fed batch continuous culture. For many applications, however, it is desirable to grow the microbes over extended period during which the substrate concentration and other condition remains constant and the cell grows at a constant, fully acylmatized potential rate on the effluent in question. Such a situation has been achieved by the frequent transfer of growing microbes from the base inoculum to fresh growth medium. In practice, this is achieved by a constant addition of fresh effluent to the growing microbes and concomitant withdrawal of equal volume of the growing microbial culture. This type of microbial growth is referred to as a continuous culture. In continuous culture, the culture volume that is either sterile or compromised of a microorganism is continuously fed into the system to maintain the steady state. The product is also drawn continuously from the reactor. The defining characteristics of a continuous culture is a perpetual feeding process. The reaction variables and control parameters remains consistent, establishing a time constant state within the reactor. This result is continuous productivity and output. Continuous versus batch culture. There are several major advantages of using the continuous bioreactor as opposed to the batch mode. First, a continuous reaction offers increased opportunity for system investigation and analysis because the variable remains unchanged. A benchmark can be determined for the process result, and then the effect of each minor changes to physical or chemical variables can be evaluated. Also, by changing the growth limiting nutrient, the changes in cell composition and metabolic activity can be tracked. The consistency of a continuous bioreactions also provides a more accurate picture of kinetic constants, maintenance energy, and true growth yield. Secondly, the continuous bioreaction provides a higher degree of control than does batch. The growth rate can be regulated and maintained for extended period by varying the dilution rate. The biomass concentration can be controlled. Secondarily, metabolite production can be sustained simultaneously along with growth. In steady state continuous bioreaction, the mixed culture can be maintained using chemostat culture, unlike in batch bioreactions, where one organism usually outgrows another. The third advantage is the quality of the product. Because the steady state of continuous bioreaction, the results are not only more reliable but also more easily reproducible. This process also results in higher productivity per unit volume because time consuming tasks such as cleaning and sterilization are unnecessary. Along with the strength of continuous bioreactions, there are inherent disadvantages that may make this process unsuitable for some type of bioreactions. For example, one challenge lies in controlling the production of some non-growth related products. For this reason, the continuous process often requires fed batch culturing and continuous nutrient supply. Another problem is that the original product strain can be lost over time if it is overtaken by faster growing one. The type of the graph the figure the growth shown by the cell growing in A batch and B continuous culture. The batch culture, a finite amount of nutrient medium is present, and growth of cells is when a essential nutrient is depleted. A lag phase, B log phase, C stationary phase. In continuous culture, cells are constantly applied with nutrient because of the inflow of fresh medium. Types of continuous culture. There are two main types of continuous culture, namely chemostat and turbidostat. The chemostat is a continuous culture in which growth rate is limited by the rate of nutrient supply, the flow rate of the feed nutrient medium, and the liquid volume in the fermenter are kept constant. The rate of self growth will then adjust itself to the substrate concentration, which depends on the feed rate and the substrate consumption by the growing cell. On the other hand, in the turbidostat, the liquid volume in the fermenter and the liquid turbidity, which varies with the cell concentration, are kept constant by adjusting the liquid flow rate. Continuous growth kinetics. As with batch culture, the specific rate at which the microorganism growth is continuous culture is controlled by availability of the rate limiting nutrients. Therefore, the rate of addition of fresh medium controlled the rate at which the microorganisms grow. However, the actual rate of growth depends not only on the volumetric flow rate of the medium into the reactor but also on the dilution rate. Therefore, capital D is equal to F divided by capital V, where D is equal to dilution rate expressed in the unit H minus 1. It is the reciprocal of the mean resident time. F is equal to flow, capital L divided by small h. V is equal to reactor volume, capital L. The net change in the cell concentration over the time period may be expressed as a D into capital X divided by D into small t. That is equal to rate of growth in reactor, rate of loss from reactor washout, or D into capital X divided by dt is equal to mu into capital X minus capital D into capital X. For steady state condition, the rate of growth is equal to rate of loss, hence small d into capital X divided by dt is equal to 0. Therefore, mu x is equal to dx and mu is equal to d. Consequently, under constant physical and chemical operation condition, that is under steady state condition, the specific growth rate of microorganism is dependent on the operating dilution rate up to a maximum value equal to mu max. If the dilution rate is increased above mu max, the complete washout of the cell occurs, as the cell has insufficient the time to double before being washed out of the reactor via the overflow. The point at which this is just avoided is referred to as the clinical dilution rate, D CRIT. For any given dilution rate under steady state condition, the residual substrate concentration in the reactor can be predicted by substituting capital D from the Monod equation. Therefore, capital D is equal to mu max into SF divided by Ks plus SR, where SF is the steady state residual substrate concentration in the reactor at a fixed dilution rate. Rearrangement gives capital D into Ks plus Kt is equal to mu max into St, or dks plus dkt is equal to mu max into SF. Dividing by SF then gives dks divided by dk divided by SF is plus capital D is equal to mu max. Hence, SF is equal to dks divided by mu max minus capital D. Consequently, the residual substrate concentration in the reactor is controlled by dilution. Any alteration to this dilution rate results in a change in growth rate of the cell that will be dependent on the substrate availability at a new dilution rate. Thus, growth is controlled by the availability of rate limiting nutrition. This system, where the concentration of the rate limiting nutrient entering the system is fixed, is often described as a chemostat, as opposed to operate as a turbidostat, where nutrient is the medium and not limiting. In turbidostat, the turbidity of the culture is monitored and maintained at a constant rate by regulating the dilution rate. That is, cell concentration is held constant. The concentration of biomass or microbial metabolite is a continuous fermenter under steady state condition can be related to the yield coefficient as described in the batch fermenter section. The inserting the equation for residual substrate into the biomass or a metabolic product yield coefficient equation gives, in this case for steady state biomass, x bar is equal to y x bar s into SR minus dks divided by mu max minus d, where SR is the substrate concentration of the infalling medium. Therefore, x bar is equal to y x bar s into SR minus s into smaller. Therefore, the biomass concentration under steady state condition is controlled by the substrate concentration of inflowing medium, and the operating dilution rate. Under non-inhibitory condition where there is no substrate or product inhibition, the higher the feed concentration, the greater the biomass concentration, and the residual substrate concentration remains constant. However, the higher the dilution rate, faster the cell growth, which results in a simultaneous increase in the residual substrate concentration and a consequent reduction in the steady state biomass concentration. As capital D approaches maximum, the biomass concentration becomes even lower, yet the cells grow faster and there is a concurrent increase in the residual substrate concentration. Objective type questions. Which of the following is not a product of fermentation? Oxygen. The fermentation is a metabolic process that consumes sugar in absence of oxygen. The product are organic acid, gases, and alcohol. It occurs in yeast and bacteria, also in oxygen-starved muscle cells, as in the case of lactic acid fermentation. 2. When energy depleted elements associated with the proton are accepted by an organic molecules, the process is called fermentation. Alcoholic fermentation is carried out by yeast known as Saccharomyces cerevisiae. Saccharomyces cerevisiae is a species of yeast. It has been instrumental to wine making, baking, and brewing since the ancient time. It is believed to have been originally isolated from the skin of grapes. One can see the yeast as a component of a thin white film on skin of some dark-colored fruits such as plums. It exists among the waxes of cuticles. The first living being on earth were anaerobic because they evolved in deep seas. It is estimated with the help of fossil record that life was originated approximately 3.6 billion years ago in deep sea. According to the recent and most popular hypothesis, life was originated at deep sea hydrothermal vents. The environment is anaerobic at a deep sea level. As number of photoautotrophs evolved and the increased oxygen was liberated in sea and atmosphere, which causes evolution of aerobic organisms. Major stimulus for spore formation in bacteria is nutrition limitation. The ability to produce endospore is normally never expressed during the active phase of growth in bacteria. It is expressed only when the vegetative growth reaches the stationary phase due to the nutrition limitation. It is now believed that the spore formation is controlled by protein metabolism of cell. The entire process of sporulation is completed 18 to 20 hours.